Sample problem 19.5. Calculate the equilibrium constant for the following reaction at 25 degrees C. Okay? So in this example, the reaction is tin plus copper 2, 2 copper 2, becoming tin 2 plus 2 copper 1. So I've written down here the two half reactions from table 19.1, which show the equations that we need to be able to calculate this. So the first thing to do is to figure out which one's the cathode and which one's the anode. What we're going to do is we're going to calculate the cell potential. And recall the cell potential, is the cathode reduction potential. So we use the standard reduction potential for the cathode, and we subtract from that the standard reduction potential for the anode. So we have to figure out which one's the cathode, which one's the anode. The cathode is the one that's reduction. Remember, reduction is cathode, and the anode is oxidation. A and O, both vowels. So the tin, Sn, becomes Sn2 plus. That's oxidation, right? It became positive, so it lost electrons. So this is going to be the anode. The copper 2 is becoming copper 1, less positive. That means it's gaining electrons. That's reduction, so that's the cathode. Okay, so now we've identified. So now the standard cell potential would be the cathode. So that would be 0.15 volts minus the anode, which is minus 0.14 volts. So that's 0.29 volts, okay? So we now have the standard cell potential. Now we can come back. There's several equations we can use, but we're going to use equation 19.5, which says that the standard cell potential related to the equilibrium constant is 0.0592 over n in the units of volts. I'll put a V there for volts, times log K. All right? So we know what the standard cell potential is. It's 0.29 volts. So let's just rearrange this equation algebraically to figure out what K is. We multiply both sides by n. So n times E cell. Multiply the right side by n, and you get 0.0592 times the log of k. So we're getting there, right? Now we're trying to find k, so we're going to divide both sides by 0.0592. So we have n times E cell over 0.0592. Okay, now E cell is in volts also, right? So those units are going to cancel. That would be equal to log k. So let's just first find log k, and then we'll figure out what k is from that. So we need to know what n is. But if you look at the equation, here's what happens. Tin has 2 electrons. Copper only has 1, but it's 2 coppers, right? So it's 2 coppers, 2 electrons, 2 coppers. You might think, hey, isn't that going to change this? Wouldn't we multiply that by 2? We do that for many different things, right? Delta G, delta S, delta H. Not for E, not for cell potential or for reduction potentials. We don't multiply it. And the reason is, even though you're multiplying this by 2, you're doing it for twice as many electrons. And the voltage here is the amount of energy per coulomb. So if you're doubling the coulombs, you would double Q, but since you're doubling the material, you would also be doubling the energy. So if you double the energy, but then you double the charge, they counteract each other, so it's still the same. It's an intensive property, essentially. So now we can go ahead and plug these numbers in. Okay, let me see if we can do that down here. So 2, and then we have 0.29 joules per... Let's just leave it in volts, actually, since we have the 0.0592 in volts. and that's equal to log k. All right? So 2 times 0.29 divided by 0.0592. And you get 9.79 or maybe 9.80. Now remember, that's log k. That's not k, that's log k, right? So we have to do the inverse. Remember, if I'm going to write it this way, if you have the log of x, and let's say that's equal to n, x is going to be the anti-log, 10 to the n. Okay, so we're going to have 10 to the 9.80 equals k. So let's go ahead and plug that in. Oh, I could have left that in there. So now this calculator doesn't have that function, so let's do it this way, 9.8, 10 to the x, and you get 6.3 times 10 to the 9. Of course, that's unitless because it's a k, right? So we have to ask ourselves, is that a big number or a small number? 10 to the 9, right? That's large, very large, right? That means you have a lot of products and not very much reactance. So what happens is the larger E cell is, the larger K is going to be. So the fact that we get 0.29 volts, a positive 0.29 volts, means that we're going to have a pretty large value of K here, 6.3 times 10 to the 9.